So, coming back to our thermal desorption, what is done is the following. So, you sample in a tube wherever, in the usual way you attach it to a pump, then bring this sample. This tube is brought to a what is called, now it is called as an automated thermal desorption unit. It is an accessory to a GC, it is kept before a GC. It does not have to be a GC, it can be anything, any analytical instrument. It is an accessory before an analytical instrument, the processing accessory. And so, this thermal desorption tube is placed in this, in a heated chamber or jacket or whatever. Okay. And it needs to go to an analytical instrument. So, let us say it needs to go to a GC, for example, assume that it is going to a GC. So, this tube, when you heat it to very high temperature, what will happen is it will all come out, the desorption will happen, but it cannot stay there, it has to be taken out quickly. So, what we do, this is what we do is we do flash desorption. Flash desorption means it is very quick, it happens very quickly, the temperature just shoots up very fast, everything comes off in one shot. If you are doing slow temperature increase, little by little it will come, the absorption is changing slowly, but you want all of it to come at once. Why do you want all of it to come at once? Because when you are sending a gas here to sweep everything out, you want the volume of the sample to be as small as possible, because now you are going to inject it into a GC. You don't, if you recall the GC, our injection is very quick, we are injecting a pulse there. So, we want it to be as close as possible to a pulse, otherwise separations will have a problem. In sample injection, your sample chromatography retention time will change and all that. So, it is very difficult to manage it. So, to the extent possible they try to do this as quickly as possible. So, a very interesting system, a lot of chemical engineering concepts go into this, and how quickly you can convert this into a pulse sample. So, there is usually a sweep gas, it is essentially that is what it does, it sweeps it, whatever is now desorbed, it just takes it, flushes it out. It is usually the carrier gas that is used in the GC. You do not want something else mixing with it, you are using argon or helium or nitrogen there, you use the same thing here. So, it is usually the carrier gas in the GC, and it goes into the GC. How can it go into the GC? Now, GC has what is called as, you can have an accessory there when you are doing gas sampling. I did not discuss this there. When you do gas sampling, you can have what is called as a sample loop. The sample loop is the holding place for the sample. You are sending in certain concentration, and you would like this sample loop to hold all the sample that you are bringing. So, this is important, because what you measure in the GC depends on what you are injecting, and what you are desorbing, it has to be in a finite well defined volume, so that you know what that volume is, you know what the sample volume is, otherwise you do not know what you are injecting, what is coming out, and all this is a big mess. So, this is all carefully calibrated and done. So, the sample loop will allow you to keep this in place. Okay. Let us not get into sample looping, you can go and read about it. You can type GC sample loops and the schematics for that will come. It is a very neat system where there are 6 ports, and the sample loop essentially will go in, and there is a small loop. This is a loop, this is a certain volume of this loop, depending on, this is the injection volume. You can have it as big as you want, 100 microliters, 1 ml, whatever. And the other part of the system, there is a GC gas coming in, and it goes to this is a carrier gas coming in from another cylinder, and it goes to the GC somewhere. What happens is when you switch, there is a certain configuration of this where it is called as a loading cycle. When you switch, this GC gas will take the sample loop and go to GC. So, that is what will happen. I am not drawing it here, but there is called as a rotary this thing. So, there is a I will not draw it here, we will just leave it like this. Go and read about sample loops. I will put it up out of the context here. So, it is possible to do it. So, people do it, and calibration now has to be done on this basis. When you are doing ATD, you have to calibrate like this, which means that I have to inject a known concentration of gas. Calibration now becomes very, very difficult, because now if you are calibrating a concentration, you have to do it on the context of this one and all. So, you have to do some adjustments to your calibration. If you want to use an older calibration, you have to make sure that it corresponds to this and all that. So, separately. But the idea here is you are now eliminating one processing step, manual processing step. You are automating everything, so that your hope is that things are. This is especially good for what is called as volatile organic compounds. Or VOCs, basically which compounds which have high volatility, high vapor pressure, very low KOW, they are very likely things like benzene, toluene, all those things which classify under VOC. There is another application of this kind of system is in what is called, when you are doing analysis of VOCs in water. Suppose you want to analyze benzene in water, the Henry's constant of benzene in water is very high. So, when you are doing all this extraction, the moment you take sample is constantly going out. Okay. So, one of the things people do is when you are extracting, again there is the chance of losses are quite high. So, people do not do liquid extraction for VOCs. They use another technique called as purge and trap. You will see this in the methods that you are using. This is a sample processing accessory. What this does is it takes the water sample directly and it purges it. You purge with nitrogen gas is released. When nitrogen gas is flushing out all the volatiles in the system, you are stripping the water. This is the water sample. This is water plus analyte, analyte plus nitrogen, both of them are coming out. Again nitrogen or anything, or helium or argon, whatever you are using. This comes out, you are basically extracting, but you are not extracting using solvent, you are extracting using the gas, vapor phase, because that is favorable. This is a volatile component anyway, it is coming out. Now at this point this becomes like a vapor sample, air sample. Now what do you do? Automated, you put a small thermal desorption tube here. We are doing the adsorption here. It goes in and sits here. This is trap. This is the purge. We trap it until all of it is purged. You purge it for 15 minutes, 20 minutes, half an hour, whatever time you determine that. This is a mass transfer problem. You know how long you need to purge it depends on what is the concentration, what is the flow rate of the bubbles, and what is the size of bubbles and all that. You just purge everything as and then you go and trap it. You trap it. Once you trap it, the trapping cycle is done. Then you do what we did in the thermal desorption. You do thermal desorption after that. And then it goes to a GC or a GCMS or whatever through a sampling loop. Again, it has to go through a sample loop to do this. So, the accessories which are very useful in analyzing this. So, all of these are directed towards only one thing, all the accessories. We are trying to increase our confidence in our analysis. So, quality control and quality analysis is the focus in most of these methodologies that are developed for these kind of things. So, we will just go over quickly. So, this is the other type of samples. So, it is something called as passive samplers. This is a new thing. This is not a standard method, it is still under development. So, this is an equilibrium based sampler, which means that in all the other things what we have done is we take a sample of air, we know what is the volume of air, and we extract whatever is there, and that we exactly get concentration, mass by volume. Yeah. Here in some cases, for example, if you want to take if you want to take ambient air samples in the way we described just now, what is called as active sampling. active sampling is where I have actively I am pulling in a certain volume of air. But the problem is I need a pump, sometimes I need electricity, sometimes I need somebody there, and some things may be stolen and all that. So the logistical problems are there. So what people have come up with is what is called as a passive sampler. You put hundreds of these passive samplers, which means it's just some matrix, some substrate, and it comes to equilibrium with the ambient air or ambient water, wherever. You put it in water, you put it in air, and this is one such thing. So it again works on, it's an equilibrium based method, which means at the end of some period you take it out, you assume, you find out if it is in equilibrium with something else, with the ambient air, and you extract. So all the work is in a laboratory, in a processing facility, but there is nothing else in the field. You can have hundreds of these things. You bring it back to a lab and you find out what is the concentration on the so essentially what we are doing is in this case we are using a partition constant. We are using some other material. We are using some substrate, some solid. So we have a partition constant here, which is Ka42 or Ka41. If we know this number, this equals WA4 divided by rho A2 or WA4 divided by rho A1. We measure this, we know this, we can calculate this number. This is very useful for getting long term average concentrations of materials, and it is also cheap when it is easier for people to find. So people use this to find out, especially when the flow is all not very difficult to manage it and all that.
But conditions will change also.
Yes, so it's equilibrium. So it's long term average. So you cannot use it like a daily average and all that. It's a long term average. It's there. It's useful for processes which are the interpretation of this is that, say for example you have a lake or a river or an ocean. It's there for a long time. Things are not going to change over 2 days or 3 days. This is a long term process. Similarly with atmosphere also. So atmosphere, your long term average, exposure average, we are talking about 30 years, 40 years, 50 years and all that. So things don't change very rapidly. What we are talking about is something, pollutant is entering, mixing, and this pattern stays for a while until you make a drastic change. Suppose all of a sudden if I say I am removing all vehicles today, it will take about a month for everything to reset to go to some other value, because there is already some concentration that might get for it to get flushed out. So this is good for those kind of, you can't use this to suggest that is the other end, right? We are on one hand we are saying we are not happy with 24-hour averages, we want to go real time. This is the other extreme, but this is sometimes useful because it's very cheap to do outside. You see that logistically it's very difficult to go and install something, especially in a place like this. People will come and steal components and go away. So finding electricity is a problem. You need batteries, which means battery operated things are again expensive. You have to charge them, you have to bring it back. All these issues are there. This one doesn't have that. But as is the rule generally with all these things, the more money you spend, the less information you get. But if you can use less information and smartly, then you have to find where your objective is based on that. So this is one other thing. I'll just finish up in a minute. Yeah, there are various kinds of passive sampling devices. People have worked with a lot of things. This is used in indoor air pollution a lot. People use it to find out what is passive smoking. People in restaurants and bars and all that. So they have this thing sitting here. And there are some standard methods for measurement of the pollutants like sulfur dioxide and nitrogen oxides. So normally the technique that is used for the priority gases SO2, NO2, you you can impinge it, you can collect it in a solution and measure it. There is a chemical method for doing it, it is all there in the standard methods. The other option is you have some equipment which does that. There are equipments which use UV fluorescence and things like that. Okay. So, it is all there in this, just go and read it. I think there is nothing extra that I can. So, we have a little bit of balance material remaining in the analysis. So, we are looking at analysis of different species. Let's just summarize that. PM and vapor. So, the organic analysis, let us just summarize it, is we have something called OCEC, organic carbon, elemental carbon. This is done using an instrument which is called as the OCEC analyzer. What they do here is they this is similar to the GC for one section of this thing. So, as I mentioned earlier, the OCEC instrument itself works in terms of the OC component is all organic compounds which have some structure, some CHON. The EC component is what is called as elemental carbon. So, this portion can be you can combust it, you can oxidize it, like the organic carbon analyzer we talked about long back, what is called as total organic carbon. So, you combust it and then whatever comes out you measure the CO2 or CO using infrared. Instead here what they do is they oxidize it, you get carbon dioxide or carbon monoxide. This is converted back to methane using a reduction reaction. So, this methane can be detected using a flame ionization detector. The flame ionization detector is very sensitive. So, and you can use a GC kind of system to without the chromatography. There is no chromatography, but what it does is this is a detector used in the GC. So, they take the sample of the particulate matter on the filter directly. So, you collect a sample on a filter paper, you take a small amount of the filter paper, small part of this thing, and you heat it. So, you heat it to different these things, you heat it temperature versus time, you heat it at say some 100 degrees, then you increase it to 200, then you increase it to 300 and increase it to 400 and increase it to 500. So, each temperature you keep it for some time. Every time you do this, corresponding to this you get a signal in the this thing. So, 100 you will get a signal, and then you will get some signal in the 200, then you will get some signal in the 300, then you will get some signal in the 400 and 500. What this corresponds is the amount so, the amount of this red signal indicates the amount of material organic carbon which will come out, which will volatilize at that particular temperature. So, you are taking fractions like we do not have any idea what this chemical specifically is, but we know that this is all constitutes what is constitutes organic carbon. So, 500 degrees it will burn off, it will combust, there is it's just burning off with oxygen, and it is coming out and then it is converted to methane, and that methane is measured. So, you can calibrate it by adding a known amount of organic carbon, and it is measured in terms of signal for methane in the end. So, the calibration is done like that. Beyond 500 degrees it is used, an optical method is used along at higher temperature, it goes up to 900 degrees centigrade. From 500 to the up to less than about 550 degrees centigrade is the organic carbon. Somewhere around this 550 to about 900 degrees centigrade is the elemental carbon, because this does not, it is carbon, it will not become carbon dioxide or anything, it will stay as it is as soot. and this is measured. Since it is not going to form anything else, there is another method of measurement which is optical at that high temperature. So, what is reported as different fractions of organic carbon and different fractions of elemental carbon, but all the elemental carbon can be clubbed in one group. And so people use this data of OCEC, the ratio of organic carbon elemental carbon, to look at where the source could be. So if the elemental carbon is high, the source is very likely to be from combustion, diesel combustion and all that, which forms soot, carbon, elemental carbon. Some combustion sources are very specifically, they form soot. So you know that if the OCEC ratio is different in different places, you will know that possibly the source contributing to air pollution in that area is coming from this source. So based on profiles of various sources, you can get information regarding what is the source contribution, which source is contributing to air pollution in that given area. So this is one instrument which is a very specialized instrument. So here, because this filter paper is directly put into the instrument and it has to withstand temperatures of up to 1000 degrees, this filter, we use quartz filter paper. So we had mentioned in the previous class that we use quartz, Teflon, nylon, different materials. The quartz is specifically used for the organic carbon, elemental carbon analysis.